Now we are going to go through two key features of MobileNet-v2, and they are inverted residuals and linear bottleneck. So first, recap the concept of the ResNet. Here you can see that inside the ResNet, there is a skip connection connected the beginning and the end of the residual blocks. And if you look at the number of channels here, you can see that the ResNet have a wide, narrow, wide structure. And the MobileNet-v2 is kind of like a combination of depth-wise convolution and ResNet. Here you can see there are three layers inside the inverted residual blocks. The first is the expansion layer to increase the number of channels. The second layer is a 3x3 depth-wise convolution layer, and the last layer is a 1x1 projection layer that reduces the number of channels. So unlike the residual block, the inverted residual block have a narrow, wide, narrow structure. We are doing this because when we apply a convolution layer to filter the data, we want to do it on high dimensional data in order to extract enough useful information. So that's why we first use the expansion layer to uncompress the data. So comparing to the residual block, original residual block, the inverted residual block have fewer parameters thanks to the depth-wise convolution layer. And it also have better performance comparing to the original ResNet and the network without residual block. And the second feature is the linear bottleneck. So the activation function in ReLU is an essential part of the neural network. However, the linear activation function like ReLU can cause serious information loss when the input have very low dimension. So if you look at the inverted residual blocks here, you can see that we use the expansion layer to uncompress the data and filter the data. So in these two layers, in the first two layers, the data is in high dimension and it's okay to use ReLU. However, in the last layer, the projection layer, we compress data and decrease the number of channels. The author think that if you use ReLU here, it will cause serious information loss. So the solution is instead of using linear activation function, we use a linear activation function here. So here we build the bottleneck by ourselves. Here you can see that after a projection layer, 1x1 projection layer, we use a linear activation function. And comparing to using ReLU 6 in bottleneck, a linear bottleneck have better performance as well.
After introducing the architectures of MobileNet-v2, we implement a demo to demonstrate our modules by using transfer learning on sign language digit datasets. Besides modifying the output layer from 1000 classes to 10 classes, we also freeze the first half of mode and only trains 10th to 16th button block, since the pre-trained model has already learned lots of edges and corners details in the first half of it. All we need to do is train the last half of mode to classify the image. It took 20 minutes to train on GPU in order to get our desired result. You can see further details in our notebook.
So in order to show the effect of MobileNet-2, we visualize the training process. Firstly, we use feature maps to show the bitwise convolution in one block. And also we show the image of different photo blocks in different stages. And after that, we use sensor maps and gradient scene heat map to demonstrate the feature selection and classification of MobileNet-2. And finally, we visualize the process of testing MobileNet-2. We draw the accuracy and the loss curves of its training and validation. And at the same time, we use the confusion matrix to view the classification of 0 to 9 gestures. And from the results, all the images in the test data are correctly classified, and this proves that MobileNet-2 has strong classification performance and while reducing large amount of parameters.